All right, well, we'll start the seminar after ending our Colorado Rockies talk. Very pleased to welcome Jordan Powers. He's here this week and giving the seminar. It's a special seminar time, obviously, since it's Wednesday at 3 o'clock. Jordan got his undergraduate degree at the University of Virginia and got his law degree actually at Stanford after that, and then went into atmospheric sciences, the University of Washington, got his master's and PhD studying under Dick Reed. So he's had very broad, I guess. So he came to NCAR first in 1992 as a student summer visitor, and later did the graduate visitor program and was an ASP postdoc. Since the mid-90s, he's been working in M-Cubed in model-based research in several projects related to model development, application, and management. Project management involves this pretty long list of models: MM5, WRF, MPAS, CESM, and SEMA, which is why he's in town this week. There's a SEMA meeting. And today's talk is going to be on results from research done in the context of the AMPS program, which is the Antarctic Mesoscale Prediction System program. AMPS is NWP conducted in support of the weather forecasting for the United States Antarctic program since 2000, and I'm sure we'll hear a lot more about that. Okay, welcome.
Thanks, Hugh. It's good to be back here. 1992, and my host was Bill, Dr. Bill Kuo. So it's really great to see you here, Bill. We made it. Okay. Well, we'll get to it today. I'm going to present results to date on an event that became of interest to me over 10 years ago, and it's one that a long-standing colleague of mine did the original work on, and we'll look at results from his paper. It's Dr. David Bromwich of Ohio State, and we were going to submit a proposal on this circa 2017, and the winds weren't favorable back then, so we didn't do it. But I decided to pick this up on my own while I still had time and resources here at NCAR to give it a shot. So this is an Antarctic mass loss event that I will describe in just a moment, and I'm applying MPAS, which is our new flagship model in MQ. And as I'll try to show, I think MPAS is really well suited for this problem. Here we go. So background, when was this? This was a while ago. This occurred from June to July of 1988. It was characterized by, I'm trying to find here's the mouse. Significant surface pressure decreases across Antarctica. And for those in the audience who may not be in meteorology, this simply reflects, or the pressure reflects the mass in the atmosphere, the column above it. The weight of the atmosphere translates to the surface pressure. So there were significant decreases in the seminal study, and the one that identified it was Parish and Bromwich 98, a case study of Antarctic katabatic wind interaction with large-scale forcing, and I'll abbreviate this as PB98. I want to credit them by using a number of figures from their paper. And I will contrast some of their results and figures with modern data sets and tools. And part of my interest in this is to see what the application of modern data and tools, i.e. MPAS, can tell us about the event and reveal about it. So the period involved was the 28th of June to the 4th of July. Antarctic surface pressure decreases per PB98 were analyzed in excess of 20 millibars, and these occurred in conjunction with outflows from the continent. On the lower right here, and I apologize, this room has a screen at low levels, but this is from PB98. It's an analysis of surface pressure changes for 2 days from the 29th of June to the 1st of July of '88, and the solid contours are pressure losses. So you can see virtually the whole continent of Antarctica, the outline is there, is under negative contours. So it really is a continental scale event. The flip side of the pressure losses over Antarctica were increases in pressure on average in the mid-latitudes and into the subtropics. So this reflects a transport of mass. What happens when the pressure decreased in one part of the planet, it went to another, and we'll see this in their analyses. This analysis here was based on ECMWF 2.5 degree data sets, which were state-of-the-art at the time in the the middle part of the 90s when they started this. But this has been superseded in our modern standard. At least one of them is ERA 5. So that's one of the tools I'm going to apply. ERA 5 at 31 kilometer equivalent grid spacing and MPAS. Before I get too far into it, I'll show you Antarctica because I'm going to refer to a bunch of places around the continent. This first bullet here on the upper right, Antarctica is an elevated landmass. It's the highest continent. It's also the coldest and the windiest, and I believe the driest. On the left is a plot of the continent. South Pole is in the middle in this plot. It's actually at over 2,800 meters. People might not realize how high Antarctica is. There's another high area to the right of it in this plot, or to the left rather, to the right from your perspective. Dome A at over 4,000. In the lower right of this plot, trying to put the mouse down there, Dome C in excess of 32. So this broad area from Dome A to Dome C, including the pole, is called the plateau, or just the Antarctic Plateau. Some of the areas of interest and that'll feature in this case are the Ross Ice Shelf in the bottom middle of this plot. That is permanent ice over the sea. It's about 50 to 100 meters in elevation above sea level. And then south of that, you get into the landmass. The Ross Sea is a prominent embayment to the north of that. Remember, things are kind of backwards from your normal perspective in the northern hemisphere, but that's to the north. And that is the location of a significant surface cyclone, which is helping drive this event. Marie Birdland is to the left of the Ross Ice Shelf in your view. We'll see that. Queen Maud Land up here around 0 degrees longitude. I'm sorry about that. Amory Ice Shelf off here about 45 east is a prominent outflow channel. And Adelie Land to the bottom right of that. I'll go back here, and I forgot. I said the whole continent had mass loss, and it does. The maximum analyzed values here were at in excess of 20 millibars over this region called Marie Birdland. Now that's just a caveat, is that's from that initial ECMWF analysis available at the time. We'll see whether that changes with modern data. Surface pressures across the southern hemisphere high and middle latitudes, they change cyclically during the year and actually on a semi-annual time scale in something called the Semiannual Oscillation. This has been written about a lot, and it's been looked at by a number of NCAR authors, and I wanted to point those out here. Harry Van Loon, 1967, that's one of the initial papers describing it and talking about it. Jerry Meal has written about it multiple times, and Jim Hurl has as well, and Jim used to be the director of NCAR. This event occurs in a subcycle of the SAO, and we'll see that in a plot or two. The SAO is a response to seasonal variations of the sunlight down there. It's completely absent from Antarctica for part of the year, and then it comes back, so there's heating and cooling during the year. That induces changes in the mid-tropospheric temperature gradients, i.e. the baroclinicity. That helps to support systems, cyclonic systems on what is called the circumpolar trough, which is shown in the left here, a band of about 50 to 65 south that features climatological consistent low activity. I apologize for jumping from slides. It's very sensitive, this touchpad. These plots here are surface obs for the event. So they actually show the pressure loss and part of the SAO. So from left to top left is Dome C, top right is South Pole, bottom left is D10, and then bottom right is a place called Terra Nova Bay. Sorry to pop back, but these places are here. Pole, you know, is in the center of Antarctica. I wish I could get better access. There's Dome C down here in the lower right. Terra Nova is down in the bottom middle, and D10 is bottom right. So at Dome C, upper left plot, first thing you'll notice, and this is a period from June to July of 1988, it's the surface pressure at this location. I put a dot dashed trend line through there. That's the SAO subcycle. And the event itself is that circled area. It's a 16 millibar pressure fall at Dome C. On the upper right is South Pole. There's the event circled. It's 26 millibars, so it's of higher amplitude. The lower left is D10, and that's a 30 millibar pressure decrease. And on the right, on the bottom, is Terra Nova. That's 28. This mass loss event is a higher amplitude event within the SAO subcycle. These observed falls in these OBS plots are in excess of 25 millibars. So these are greater than the signals seen in the ECMWF 2.5 degree analysis. So we would expect that those coarse analyses may not resolve or fully account for the observations at sites. And the geographic spread of these observations and their magnitudes shows a wider distribution of greater amplitude falls than those first analyses. This is the synoptic environment of this event, and these are plots from PB98. On the left are two SLP plots from 0Z on the 29th on the top. That's when the event is starting to ramp up. There is a prominent low in the Ross Sea. It's at 963. To the top of this plot, there's a low off of Queen Maud Land, inducing flow off there at 973. And off to the right, that's around 90 east, the Amory Ice Shelf airstream, 976. A couple days later in the bottom plot, sorry for those who can't fully see it, the low in the Ross Sea now has two centers. One of them is down to 958, so they're deep systems. We'll see the circulation of that in just a moment. In the top right of the plot, we have this Queen Maud Land low. It's filled a bit and migrated eastward, and that other low is gone. On the right are mean surface winds from PB98 for 2 days or 4 days during this event, and they show the streamlines of the airflow from the continent. At the bottom of this plot is the Ross Ice Shelf airstream. It's a confluence of streamlines. It is a climatological channel for air flowing off the continent. Often these flows are called katabatic, but it's recognized in the literature that they're not purely katabatic because there are always synoptic lows helping to force them. But the Ross Ice Shelf airstream is prominent in this event. It was not called the RAS, that's the abbreviation for Ross Ice Shelf airstream, when this paper was written, to give you, put its age in perspective. But it was certainly identified by Parish and Bromwich here and in other places. That term RAS, and I'll use that name later on, just came into coinage later. There's flow off East Antarctica to the top of this plot, prominent flow, Queen Maud Land, and then off of Adelie Land, a lot of flow as well. I will get into the MPAS modeling results now and set it up with this. Fortunately for NCAR, I don't have to give a lot of background on MPAS, but the model for prediction across scales is a global model designed for operation down to the cloud resolving or non-hydrostatic scales. I'm not using it at that scale here. I'm not having grids, I don't have grid sizes that fine. But still, it's well suited for this problem because of its global reach. I have an event of hemispheric reach, as we'll see. I don't have to worry about boundary conditions, artificially changing things or prescribing the flows. And I can also have smooth mesh transitions. As the middle bullet here says, it's a 48-kilometer mesh globally with an 8-kilometer regional refinement over Antarctica. That's what this depicts, and thanks to Michael Duda for this. So we have higher resolution, higher density mesh over the continent, and it coarsens as you go north. This mesh spacing is actually coarser than 8 kilometers in this plot, because 8 kilometers would not be big enough to let you see the individual cells. So you can compare a 48 to 8 kilometer over the continent grid with a 2.5 degree global analysis that was used in ECMWF. So I've got well over an order of magnitude better resolution right over the continent, and at least a half an order of magnitude better res around the far parts of the globe. 51 vertical levels, and my first level above the ground is 10 meters. The other details on MPAS, I won't go through all these, but this is the mesoscale reference suite. I'm using VA231, which was the first one that had the public release of NOAA-MP. We've been using NOAA-MP in our real-time Antarctic mesoscale prediction system that Kevin Manning oversees, and I wanted to use it here. Initial conditions are coming from ERA5 reanalyses, which is 31-kilometer equivalent resolution, and it's a 6.5-day simulation beginning at 12Z on the 27th of June. Okay, now to the results. These are two plots of the surface pressure changes. The left one is PB98. We saw that. The one on the right is from MPAS. So the MPAS simulation period is the same one analyzed in PB98, a 2-day period in the event. So we'll just get right to it. PB98 had a maximum of slightly in excess of 20 millibars over Marie birdland. In contrast, the simulation, MPAS is showing 20 millibars, a bit more than that. That's Dome C, and 32 millibars over Dome A. So MPAS's simulation is significantly higher in terms of the amplitude of the event. MPAS does have pressure falls over virtually the whole continent. There's a little sliver out here to the east near 90 that has some pressure increase, but that is the counterpart to the area in PB99. There's a synoptic system out there that's moving along. But basically, MPAS is showing that it can reproduce at least this quantification of the event. It is showing us higher amplitude. Is that accurate or not? Let's compare it with ERA5. On the right is ERA5. ERA5 is showing pressure falls over a region poleward of Dome C in excess of 20 millibars and near Dome A of 32. And on the left is the MPAS simulation showing that same magnitude and pressure distribution. So MPAS reproduces these continental delta SFP, which is surface pressure change patterns. The MPAS magnitude of the event over the continent is verified. In the mid-latitudes, that is in the periphery of this plot, the changes are mostly there. If you look, for example, in the top of these plots, ERA5 analyzes a 26 millibar gain center as well as an 8 millibar gain one, and those are in the MPAS simulation. On the bottom part of the plot, in the raw sea, there's a 16 millibar area of 16 millibar gain, and that's in MPAS as well. So there's another area that's not forecast exactly with the same magnitude, but by and large, away from the continent, the pressure changes are reproduced. What about the synoptic systems at low levels helping to enhance those low-level flows? This is MPAS versus ERA5. ERA5's on the left. Sorry for all the lines, but I wanted to try to make it easier for the eyes to connect one thing to another. In the ERA5 plot at the top, I want to say I flipped the orientation of Antarctica. So 180 degrees longitude is now going to the top of the plot instead of the other convention where it's reversed. And this is the way we normally look at things for the United States Antarctic program. And most of my stuff is set up to look at things like that. That's the reason. So in ERA5, to the top of the plot, we have a 964 millibar low in the raw sea. So that's what PB98 identified as important for helping force the RAS in this case. And indeed, MPAS has simulated that. If I get the mouse there, it's at 966 in MPAS. The configuration of the trough and the low pressure area is very similar. Those extensions indicating frontal zones are there as well. So I highlight that one in yellow kind of because it's important. Off of Adelie Land in ERA5, that's up in the upper left part of this plot, there's a 978 low, 979, same position, almost identical intensity in MPAS. To the left, off of 90 East in ERA5, 968 in the analysis, 968 in MPAS. And finally, at the bottom of the plot, that's off of Queen Maud Land, that area, 965 analyzed, 959 MPAS, so a little bit different depth there. The important thing is MPAS is capturing the key systems, their positions, and basically their intensities. Even the anticyclone over the continent is there in place. So the bottom bullets say, for those who can't read them, MPAS reproduces the deep raw sea low highlighted by the original work is significant in the RAS part of the outflow. And MPAS also captures the systems around the rest of the continent, enhancing the flows. What about aloft? Well, the lower level features are lining up. We would hope the upper level support is there as well. And here we can check that. So this is 400 millibars. May seem like a strange height, but it's below the tropopause in Antarctica. where the tropopause can get down to 350 over the plateau. So I wanted to be in the troposphere. A key area is the broad area of low heights in this area where I have the mouse in the upper left of the plot as you look at it. That's from Adelie Land northeastward. That area, upper level low, is helping to force the Ross sea low. There are two centers there, and MPAS has simulated two centers. The central heights of those areas are very similar. The lower one is analyzed at 6311 and in MPAS at 6304. And the upper one is about 30 meters difference in height, so very close. This anticyclone in the upper right of the plot is there in place, same position, same configuration, and same central height. And finally, the low in the bottom of the plot off of Queen Maud Land that's helping to induce that surface low is reproduced in MPAS. You can see it, the line connecting them, same position, and very similar intensities. So MPAS has reproduced the upper level features driving this event. And I just wanted to verify that. We want to see the complete picture. We're going to have to look at the circulation through the troposphere later, so we can see that at least at this time in this view, it's accurate. This final one I'll go over pretty fast. Sometimes we're asked, well, your simulation looks good at a couple of days, but what about at 5 days or longer? The simulation actually goes for 6.5, but this is at 5 days. And it's corresponding, these lines are showing the correspondence of the surface lows in both the analysis and an MPAS. I won't go through every one of these, but the key one is up here. I have the mouse on it in the northern Ross Sea. 944 analyzed. There's a center at 945 produced by MPAS at 5 days, a little bit to the north. MPAS had produced a secondary center to the south at 954, which is just part of a broader trough in ERA 5. So MPAS developed that separately. But basically, that surface system is still in place with its associated flow in the RAS. The other system I'll point out is off of Adelie Land here. I got the mouse over it, and that is reproduced in MPAS, same position, a little bit shallower. And the anticyclone over the continent, those two highs are the same. So MPAS is good at 5 days. I'm going to switch now that we've looked at the synoptic setting and got an idea that MPAS is good with that, to actually look at the event in terms of zonally average surface pressure changes. So we have a bunch of plots here, and each one is a different latitude, and it's the zonally average changes through the period, or most of the simulation. All of these plots are time series. So on the left is 0Z on the 28th of June, and on the right is 0Z on the 4th of July. These plots do not start at the very beginning of the simulation. So they're into the simulation when the pressure falls are started. I don't look at the spin-up period here. And what do we have? So each point in one of these curves represents the difference in pressure that's zonally averaged around that indicated latitude minus the value of that at 0Z on the 28th. So they all start at 0 because it's the same time minus the same time. So for 60 south, which is in the upper left, we'll start there. And 90 south, by the way, is at the bottom in the middle. 60 south, the bottom line is that there's little change through the period. You see that blue line is mostly around 0. There's not much change through that. However, you go immediately south of that, for example, 64. I've done this every 2 degrees, but I can't show every 2 degrees. So at 64 south, you see an immediate SFP decrease compared to 0Z. And it goes down. The values of the pressure loss on the left are in millibars. This first bottom here is at it's 6 rather, and then the second one at 0Z on the 3rd of July is at about minus 7.5. So we have clear decreases at 64 south. They were also there at 62 south. So I point that out because 60 south is going to be a point of interest here. At 70 south, the one on the upper right, SFP decreases throughout this whole period. The difference between 70 and the one to the left at 64 is the amplitude. Now we're down to minus 10 millibars. You see that label? And 14 is what's hit here at 6Z on the 3rd, on the 2nd rather. In the middle on the left is 74 south, almost monotonic pressure loss through this time, down to minus 16 millibars by the end of this period. 80 south is the one next to it. even higher amplitude losses. Now we're down to minus 20 millibars here at 0Z on the 1st of July. Can't read that. Second. And then a little bit more by the end of the trace. 84 south, the amplitude is even greater. We're down to minus 24 millibars at 03Z on the 3rd of July. Finally, the bottom plot is at pole itself. It's not quite as strong, but it does show this mass loss. So the conclusions are their SFP decreases from greater than 60 south all the way to pole, and I'm calling 60 south the latitude of inflection, because if we go north of that with these plots, we see that the pressure tendency is the opposite. And these go from 54 south in the upper left to 10 south in the lower right. So at 54 south, the bottom line is there's an SFP increase. You see now the curve is rising from 0 throughout the whole period, and magenta is my convention for every place that has an increase. So at this latitude, there are increases. And the first peak here is about 3.5 millibars, and then there's a latter one that's even more. If we go north of that, the first peak is at about 4 millibars, and the latter one is about 5 or so. So there's an increase in the mass gain at this latitude. At 44 south, the gains are even greater. They're up to this first peak here, 09Z on the 1st of July, it's 6 millibars, and then it increases to the end. At 40 south, we're a little bit less, about 5.5. At 34 south, there are gains throughout this period, but they're less. At 30 south, you can see it's diminished. Likewise for 24, small SFP increase is what I conclude. That's up to about a millibar or so, but it's constant, so I'm calling that a gain. And finally, at 20 south, it's a very small SFP increase. That's my label for those that can't see it. It's about a half millibar, but because it's persistent, I'm saying it's there. And then at 10, the lower right one, there's no increase, so there's no change. So their SFP increases from 60 all the way to 20 south. So these increases go into the subtropics. The mass can be tracked in a zonal mean sense into the subtropics, and the movement of mass occurs northward over time. That refers to these arrows. If you look at 54 south, I have the mouse over it. There's a first peak there at 18Z on the 29th of June. If you look at 50 south, you see the same shape of the curve, but that peak occurs later at 12Z on the 30th. If you go to 44, which is further to the north, you see that peak is there, but it's at 09. At 40 south, it's later. At 34 south, it's later. At 30 south, it's later. I'm moving my mouse through each plot. And finally, at 24 south, it's there even later still. So there's a coherence to this mass gain in the northern hemisphere that's averaged over these latitudes. So we have this latitude, at least in the MPAS simulation, of 60 south, where things change, they inflect. You go from losses to gains. This is not, I didn't discover this. This latitude region has been described in the SAO literature well before. And these plots here are just to point that out and to show it in a slightly different context and lens. But these plots here, the two lower ones, are from Parish and Bromwich, 97. They're based on the ECMWF data sets available at the time, 2.5 degree. The one on the left has a bunch of curves for different latitudes, 90, 85, all the way up to 50 south. And what they're showing is for each point in that curve, it's the difference of the zonally average surface pressure for that month, the monthly average value, minus the value for January. So at the very beginning of this, everybody's 0. So for all these latitudes, it's the January mean value minus the January. But you go to the other months, and you're differencing different quantities, values. And what you see is that for all these latitudes, there's 60, I'm showing that with the mouse. For all latitudes 60 and poleward, there are decreases. All these values here of delta pressure are negative. And so you go through a phase of the year here where their pressure relative to the January value is less. This pattern is interrupted from March to April, depending on your latitude, but all from 60 south. And the difference from January is a little bit less. That difference decreases to June in this analysis, and then we decrease again. So this is these are SAO subcycles, and the event occurs in this red bar here. That's the time of the year when my event occurred. It doesn't occur in the context of these values because, well, it does actually, but these are 10-year averages, I should have said. These are taken from ECMWF for a 10-year period, so they're not instantaneous. But that's where it occurs within the seasonal cycle. And you see all these curves show decreases from 60 south, 50 and 55, I have my mouse over it, are increases. You can see that pattern here on the right, which is another permutation of zonal pressure change differences. But in this case, this dash curve here shows the pressure difference from the mean zonal value for April minus that of January for all these latitudes from pole to equator. And this part of the dash line that I'm highlighting is everything south of 58. And those are all pressure losses for this, this part of the year. That's this first part of this curve on the left. And then we actually see gains into the mid-latitudes and pushing into the subtropics. But it changes right there around 50. So I didn't discover this, but it's nice that MPAS has the physics and atmosphere together enough to properly simulate that. Another way to look at SFP changes is instead of, for a given latitude, all times, for all latitudes, select periods of times. And that's what these plots show. Again, I'm showing PB98 plots, one, to give them credit, but also I will be contrasting this with ERA5-based analyses. So their original plot in this format shows in the vertical surface pressure differences, the zonal values for these latitudes from pole on the left to equator on the right for different time periods. And this black curve, the bold-faced one, is the pressure change from the 29th of June to the 28th of June. And the other curves are from the labels there, the 30th and the 1st and the 2nd to the 28th. So they're differenced over different periods. This first bold-faced one in black, it shows pressure losses here, because there's the zero line, for all of the continent, essentially. There's a little bit of a gain there at pole for some reason, but pressure losses. And the losses extend to 59, if you can read that number. North of 59 south, there are pressure gains into the mid-latitudes. If we look at the curve for the 30th, the period from June 30th to June 28th, the event has amplified over the continent. It's down to minus 10 millibars here at about 82 south. There's another zone of minimum pressure, enhanced pressure loss, at around 65 or so. North of perhaps 67, buried in those curves, is the change latitude, and north of that there are gains. This is the line we're interested in is dashed, and it's up to 5 millibars at about 45 south or so. The curve for the July 2nd is dashed. It's under there. We see an amplified event, even greater losses of mass, down to 19.5 millibars at about 82 south or so. It becomes positive. We're seeing pressure gains north of about 55, and they hit about 6.5 millibars here. And the last curve is the thin, dark one. The event has continued to amplify per these analyses with a maximum of minus 21 millibars, 22 at pole. It switches at about 53 south, and north of that it's gains to about 7.5 millibars. The MPAS simulation is on the right. The curve for June 29th has this same pattern with two zones of enhanced pressure loss, one at about 67, one at about 83, which is the same as what the original analysis indicated. And the amplitudes of those pressure losses are about the same too. Our inflection point is about 61. I have a little bit more resolution here, so it's about 61, and then north of that we see the gains. Those gains are of the same amplitude as those in ECMWF. The curve for the 30th shows our two minimum structure, different latitude belts over the high latitudes. However, our amplitudes are greater. We're down to minus 12 millibars as opposed to about minus 10. So that is consistent with what we saw in the horizontal plots where MPAS and ERA5 were showing that the event is stronger than was originally analyzed on the grid scale. Pressure gains here are north of about 60 up to about 5 millibars, 4.5 rather. In the vertical, by the way, these scales are the same. So I have this purple line of 5 millibars on the plus side. That's the same in both plots, so you can directly compare. The curve for the first here actually has the greatest pressure losses compared to June 28th at 0Z in MPAS. We're down to minus 25 plus millibars at 84. That's a lot more than the ERA5 analysis. We flip over, sorry, and we gain, we're up to about 6 millibars. And the final curve, July 2nd, again, there's a zone of 2 minima, and not too much different from the analysis, except the analysis from ERA5, from ECMWF is a little stronger. So what if we compare that to the contemporary standard? ERA5 now is on the left. It's showing pressure losses over the continent. MPAS has reproduced basically the pattern and the amplitude. The crossover point is very similar. It's 60 in ERA5, 61 in the model. It gets up to about 3 millibars. So on the plus side, in the mid-latitudes, we are verified. For June 30th, we see this 2 latitude belt minimum structure. And in MPAS, it's a bit stronger here at about 84 south. MPAS shows greater pressure loss for certain periods of time when you're doing the differencing than the analysis. On the plus side, we're up to almost 5 millibars, and that was the ERA5 analyzed value. So the MPAS simulation is verifying. I won't go through all these curves, but it is quite good, except for this July 1st value, which is, shows greater pressure loss than the analysis. So the bottom lines here on the bottom are the MPAS simulation shows a largely verified surface pressure redistribution pattern across the hemisphere. The simulation shows greater SFP decreases for certain periods and latitudes, not all of them. By and large, it is verified by ERA5. And the latitude of inflection, it's a little bit broader here. You see this gray zone in ERA5 than it is in MPAS. Originally, I thought maybe the ECMWF just can't discriminate, but ERA5 shows for different times the point at which the pressure is positive or negative in that difference varies. I'll show a final view of pressure change values, and this is through the quantity of integrated surface pressure changes. What these plots show are represented by this formula on the lower left that I have the mouse over for those that can see it. But it's simply for different latitude bins, and we're using either 2.5 degree bins for ECMWF or 2 degree bins in MPAS. The pressure change for that bin for a given period of time weighted by its latitude. So it's trying to account for the increase in area represented by each latitude as you go from pole to equator. On the left is the PB98 calculation, and there's a curve here for June 30th. So this is the integrated surface pressure change for the period, as it says on the top, the 30th of June minus the 28th of June. The other curve is for the 2nd of July minus the 28th. But the curve for the 30th shows a maximum value integrated at minus 19 millibars at 58 south. And north of that, we see a decrease in this value, which is consistent with north of that there being pressure gains. So now you're offsetting that accumulated negative value that this formula produces. It flips over. This quantity becomes positive at 39 south, and then north of that, it's positive. So these gains carry not just into the mid-latitudes and into the subtropics, but into the tropics. You see this quantity is positive all the way to the equator per their data set. The other period of time is the July 2nd minus the 28th of June. And for that, because it's July 2nd and the event has amplified, the maximum value is greater. It's down to minus 34 millibars at 53 south that occurs. The crossover point is 32 south, and north of that, they're integrated gains up to 5 millibars, and these again extend into the tropics. The MPAS simulation For the June 30th period of time, maximum integrated value of minus 25 millibars. Again, at 60 south, that's consistent. So the amplitude difference there in this quantity, also reflected in the horizontal charts, is 25% greater. And that's consistent with ERA5, as we'll see in the next plot. The crossover point is 40 south, where this quantity becomes positive, much like in that earlier course analysis. And on the plus side, it carries plus 5 millibars into the tropics. The other time period, MPAS simulation is down to minus 40 millibars. It crosses over at 30 and it gets up to plus 5. So at the minimum here, the greatest integrated negative value is again about 25% greater. But it's interesting, in both of these, MPAS shows that this is an event of hemispheric impact if you consider it in this through the lens of this quantity. Finally, on this is ERA5. So what does the contemporary standard show? Left is ERA5. Maximum value for this period ending June 30th is minus 24 millibars compared to 25. In MPAS, they've got a change point or minimum point here, 58 south versus 60, very close. So MPAS is doing well in this with this metric. On the plus side, it's up to 6 millibars. ERA5 shows that, or confirms that this quantity does carry positive into the tropics. The other value for ERA5, minimum of 38 millibars compared to 40 in MPAS. So again, MPAS has this zone, this latitude belt around 84, where it's slightly stronger event, and that's what's showing up there. So the bottom lines for these types of analyses are that MPAS qualitatively reproduces the current estimates, the ERA5-based estimates of integrated surface pressure changes. MPAS's maximum amplitude of mass loss is about equal, for the earlier period considered here, ending on June 30th. It's a little bit greater for the later period. The low latitude increases are a little bit less in MPAS than the analysis from ERA5, and the integrated signal in our contemporary data set does carry into the tropics. I'm going to finish now with some thoughts on why this mass loss is happening, and I've only got a partial answer. So these plots are near-surface wind fields from ERA5 and MPAS for 0Z on the 29th of June, when the event is ramping up. And on the left is ERA5, and on the right is the simulation. So from ERA5, we see this low here where I have the mouse at the top of the plot. That's our raw sea low. There's a very strong flow coming off of the continent from the plateau, as well as West Antarctica, actually, through the RAS, the Ross Ice Shelf Airstream. So ERA5 shows that here. MPAS has captured that. There's a strong low off of Adelie Land, which is helping to pull flow off of that sector of the continent at low levels. And finally, there's a low shown in ERA5 off of Queen Maud Land, and MPAS has reproduced all of these. We got an idea of that earlier. So we have our Ross Ice Shelf Airstream, or RAS, and I want to look through that because that's a main outflow channel, and it's been identified in literature as such in different contexts. But in this context, it's a place where mass is exiting. So I'm going to look at a cross-section on this. There's a magenta line in the middle of that, pink line rather, from pole in the middle of the plot to 50 south. And I have a wedge here, and what I've done is taken every 2.5 degrees or so through their slices, and I've averaged them for a given time. And then for multiple times, I've taken that average and averaged that. So I'm really trying to get a mean look at the flow through this key Ross Ice Shelf sector for this event. And that's what's shown in the next plot. This is a meridional flow in this plane, the meridional cross-section. On the left is 50 south. I'm sorry, I wish this whole screen were higher. But on the left is 50 south. On the right is pole. And let's see. At the bottom, I've highlighted a region in yellow from about 2 kilometers and below, where there's all flow to the north. For those who can see the vectors, they're all pointing to the left, which is to the north. It is northward flow into at least to 50 south, because that's where this plot ends. So it's flow into the mid-latitudes. The RAS is the enhanced flow to perhaps 65 south to 60 south at the bottom of this plot. So as I have here on the left, in the middle, northward mass flux is indicated through the event for this key sector. Above that, in the atmosphere, in the troposphere, you see these vertical vectors. So there's a vertical component, vertical motion, and this is part of a climatological direct circulation over Antarctica, where there's upward motion, rising motion in the mean at the continental slopes, depending on where you are, or the margin of the continent if it's part of one of the sea sectors. So that is a known feature. And you can see some of the downward motion here to the left, which is over pole, and some of these other latitudes north of the pole, where there's downward motion. That's the subsidence over the continent. Aloft, you see what I'll call return flow. It's part of the direct circulation, but it's there. So it's going from north to south. So this is what the event looks like. We do have strong flow below, but we have return flow aloft. So what's different? What happens in the event compared to before the event? And this next plot gives us an idea of that. This is a difference plot of during the event minus before the event with this composite technique approach. And what it's showing is, and the periods shown are the difference of a mean flow from the 28th of June to the 1st of July minus the value through this sector on the 27th of June when this, before this starts. Again, it's the same latitudes, everything else is the same. So at low levels here, in yellow is our region that we had seen low-level northward flow. And for most of this region, there is off-continent flow. In some areas, it's enhanced. Some areas, you get zero difference, so it means that from during the event to before the event, the flow it was north before, and it either increased or it stayed north during the event. The big difference is aloft. And from the mid-troposphere on up, you see that these vectors, these resultant vectors, are now directed northward. So there's a counter-gradient circulation up there. It's diminished so that it appears to be counter-gradient. It's still going to the south, but it's a lot less than it was. And so in the net, there's uncompensated transport off-continent because you have, for some reason, a relative breakdown of the return flow aloft. I don't know why that is. So that question, I don't know. I've gotten this far. I can see why, logically, you'd lose mass at the surface because of more outflow than inflow. So I'll summarize here. We had a mass loss event back in '88. Thanks to my friend and longtime collaborator, Dave Bromwich, and Tom Parish. He used to be at the University of Wyoming, since retired. They found greater than 20 millibar grid analyzed pressure decreases. It turns out with modern data sets and modern models, we see that the pressure over large areas of the continent was in excess of 30 millibars of loss. MPAS does capture the event. It simulates the synoptic environment, which is responsible for what happens. The event amplitudes are largely verified. Sometimes they're a little bit in excess of what ERA 5 shows. The mass changes and redistributions with latitude are reproduced. In terms of event characteristics that come out from the simulation, these pressure decreases are result of uncompensated low-level outflows from most of the continent. The mass losses across the high latitudes occur in conjunction with mass gains into the mid-latitudes and the subtropics. So you can follow the mass shift into the subtropics. And in terms of an integrated quantity, kind of a mathematical construct, the increases occur into the southern hemisphere tropics. So it is, in some sense, an event of hemispheric impact. And I'll close with just another thumbs up for MPAS. I think it's a good tool for this. I guess the final comment I'll make about that is that as MPAS gets its high top version, maybe I can apply that in case there are stratospheric elements that I'm not capturing here. But the event is reproduced, so whatever's below 30 kilometers in MPAS can largely get it, because that's my model top here. So thank you.
time for questions. And the ceiling mic is on, so we don't need to ask.
Jordan, quick comment and then a question. My comment is I love to see people that use millibars in their talks rather than hectopascals. I'm a millibar man, so I'm very happy to see a brother in arms here. I hate hectopascals. My question is related to the winds, and you focus mostly on the pressure throughout, but you kind of got to the winds near the end there. What kind of wind anomalies are we talking? Like there wasn't a magnitude on the plots. I'm kind of wondering like how anomalous were the winds in this event, because 20 millibar, 30 millibars is a huge pressure drop.
Yeah, well, in the upper tropes, on the order of meters per second in the mid-troposphere, there.
Okay.
Difference. That's something I can just read the label if I blow it up here in a moment, but I don't know off the top of my head.
Yeah, if you're like at McMurdo Station or something like that, would you notice an increase in the winds associated with an event like this?
Maybe if they get above a certain threshold, they lock things down, so then you pay attention. But it's normally a windy place, and the winds are coming out of the south, which they were in this event. It's a climatological background flow that's there, but it happened to be enhanced here.
Okay.
I don't know the climatology of these things. I was asked that at in another venue, and it'd be a good master's topic, I think. Anybody have I think for a master's, a nice tractable problem of how often do these occur, these events?
So from your analysis, it appears the mass loss is consistent with the 10-year trend, right? And the question to me is, what is the trigger for this particular event? Because this is bigger than average, right, in terms of loss. So what really is the trigger for such an event?
I don't know. I look at these lows and they're deep, and they're in all sectors of the continent, but that's not unusual. I don't know whether it's something aloft that is resulting in a breakdown. In terms of the surface pressure change, I don't know what's forcing that.
I wonder if during this period you have more active Southern Ocean cyclones, because those are low pressure systems, right? It is sucking the air out of the continent.
Yeah.
And that might be interesting to look at.
Yeah, I focused right around Antarctica because I was working off of PB98 and just trying to use their tools. So this is as far as I've gotten, but that may be it. It may be greater intensity and number of other cyclones in the circumpolar trough in this week.
Yeah.
That's overwhelming the atmosphere's ability to replenish itself.
Yeah, directly along those lines, it seems like it might be useful to do zonally average circulation to see if where the cyclonic circulation is strongest and how that compares from year to year.
So what quantity might I zonally average?
Just the mean.
Horizontal wind?
Yeah.
Okay. Yeah.
Yeah, because there has to be at that scale some balance between the low and the circulation. So that might be another way of measuring, and that would get at the intensity of that strip of low pressures.
Yeah.
Do you have any idea if there is a similar process happening at the North Pole? Or is this because there's no continent there?
Yeah, so I think my short answer would be no. Some Arctic person might say, you idiot, but there's no elevated landmass. That's what Antarctica has. It's always got this katabatic flow pouring off the sides of it. It goes up from sea level to 3+ kilometers. And that's another reason why, it gets into, lows don't penetrate Antarctica that much because the vorticities, they're squashed when they go over it. So you don't see deep lows in the middle of the continent.
So that's kind of going to your question. If it's something in the lows in the Berkeley zone, we would see similar things in the northern hemisphere, right?
What if maybe some of the low systems were kind of just by happenstance positioned along with the climatological outflow regions of the continent? If they just happen to be in the right place at the right time, There are several of these climatological outflow regions, and if each of those had a low that happened to be right at the right place, could that be sort of enhancing the flow off the
It could
continents?
be like a resonance.
Yeah.
Because there's that complex in the Ross Sea, it's there for a week. It doesn't really move. And then there's one from Queen Maud Land that goes to the Amory, forcing that channel.
Yeah, it looked like when you showed the time sequence of the pressure drops, they originated more at the coast, and then at the center is delayed more than at the coast. So it seems like it originates further north and then spreads. So the dome collapses later then. At least it looked like in your time series the pressure drops more quickly earlier at
maybe.
the coast. Yeah.
Maybe that may be the place that feels it first,
Which
because
implies
the mass is leaving there and it's still coming over the top
Right.
in the return circulation.
Right.
So maybe before the return circulation, the effect of its diminishment is fully felt, where the mass loss is noticed first at the periphery.
Yeah, the center is responding to something going on further. Yeah.
I was wondering about the seasonal cycle in that PV98 plot that you showed. I can't remember, it was like maybe 2/3 of the way through. Yeah, right here. The surprising thing to me here is that it's not symmetric with this cycle. Why does it jump back up in June? Did they postulate maybe why that is? And then it decreases and reaches its minimum in August.
Yeah.
Maybe what we'd expect.
The circumpolar trough contracts and intensifies from June to September, so that's the event happens there. It also contracts December to March. I'm trying to get at what you're asking, but are you talking about the asymmetry in this?
Yeah, and the seasonal cycle. The fact that it starts to go down in April,
And then goes up.
then it goes back up, and then back down.
It's because the circumpolar trough shifts a little bit to the north.
So it's kind of
it's-
superposition of that with this inflow, outflow, and
This event,
Yeah.
is in this context. But the SAO has that stuttering because the circumpolar trough doesn't go down monotonically and retreat monotonically. And the reason that there is that irregularity is that the ocean and the atmosphere, the temperatures are not in sync. There is heat loss delay in the ocean in the cool season, and heat gain delay in the warm season. And the atmosphere responds much more quickly to the changes in the insolation. So it's tied to the differences in the response of the air and the water to changes in the insolation.
So I guess you mentioned sort of it'd be interesting to look at the climatology of these, which is that would be interesting. How much of these kind of events like this do you think might be responsible for the mass loss that occurs? Kind of because I imagine that as we kind of move into March, April, May, and especially in that kind of July, August, you just get these events where you just get these sudden mass losses, and then in the second part of the cycle where it's going back up, it's probably more of a slow buildup. Like I don't think you get rapid mass buildup when it's recovering.
Yeah, I don't know about the buildup, but you may be right that the climatological mass loss occurs in a series of steps. And these events may be the components of the subseasonal mass loss occurs in step decreases,
And then it comes back up kind of more smoothly.
But after this event, it comes back up, if you look in the ops.
How long does it take for it to recover
On the order of days.
Okay. So not too much slower than it was lost.
Yeah.
Okay. All right. There's maybe one more question, otherwise we can end.
I don't see anything on Slido either.
No. All right. Well, We'll take Jordan one more time.